Our project is about quantum cascade lasers. Quantum cascade lasers are semiconductor lasers that emit in the mid to far infrared portion of the electromagnetic spectrum.
Some important people who were involved with quantum cascade lasers are Jeremy Feist, Federico Capasso, Deborah Sivko, Carlos Satori, Albert Hutchinson, and Alfred Cho. They were the first to demonstrate the quantum cascade lasers in 1994. John Robert Woodyard was the first to demonstrate the process of doping.
Without quantum cascade lasers, it would be difficult to detect problems in our food, such as E. coli, anthrax, and mold. Also, the military uses them to help detect unknown substances.
Quantum cascade lasers are important to our daily lives because they are used in a lot of our electronics. Without them, we probably wouldn't have cell phones, laptops, televisions, etc.
Quantum cascade lasers were first demonstrated in 1994. They also led to the development of LED lights, laser diodes, semiconductor lasers, and the process of doping. Doping is a method of adding a dopant to a pure semiconductor to change its electrical properties.
N-doping is much less common because the Earth's atmosphere is oxygen-rich, thus creating an oxidizing environment. An electron-rich N-doped polymer will react immediately with elemental oxygen to de-dope the polymer. Thus, chemical N-doping must be performed in an environment of inert gas. Electrochemical N-doping is far more common in research because it is easier to exclude oxygen from a solvent in a sealed flask. However, it is unlikely that N-doped conductive polymers are available commercially.
Group 4 elements such as silicon, germanium, and silicon carbide have acceptors and donors added to them for the process of doping.
The acceptors and donors that are used for doping are from Group 3 and Group 5. These include boron, arsenic, phosphorus, and sometimes gallium. When you add the impurities or the acceptors and the donors, it allows the semiconductor to conduct more electricity.
The lasers themselves are solid, but the beam that they produce aren't any state of matter, they are just an enhanced light.
SPIE presents the Advancing the Laser series, honoring 50 years of laser achievements.
My name is Federico Capasso. I'm professor of applied physics in the School of Engineering and Applied Sciences at Harvard University. I've been there for the last 8 years after a 30-year career at Bell Laboratories. We have research ranging, I would say, from the very applied, working on application and commercialization of quantum cascade laser, next frontier of quantum cascade laser, and another very interesting area which is now again between applied and basic is plasmonics and metamaterials, and finally really on the fundamental side is the study of fundamental quantum electrodynamical forces. The quantum cascade laser was originated at Bell Labs, and I would like to say it probably was about the only place where it could have been invented. I had the privilege to work with, for many years, with Al Cho, who is the pioneer of MB, and we did this work jointly. He basically grew the material based on design that my group and myself came up with. There is a lot of knowledge of solid-state physics and quantum mechanics that went into it. So I would say this richness, this interdisciplinary nature of the work, in some sense was always the hallmark of Bell Labs. The fact is that the more we work on the quantum cascade laser, we realize it's a truly radically new laser that differs in a dramatic way from past lasers. You can design the gain spectrum so that you can have, the laser can have both an enormous tuning range or it can be designed to emit simultaneously at many different wavelengths. Lately, the biggest surprise has been, and for me it's been sort of a conceptual shock, the basic theory of the line width of the laser was worked out by Shallow and Towns in 1958, the first paper on laser. It says basically that the line width is controlled by certain formula, given the Shallow-Towns formula. In diode laser, the Shallow-Towns formula has to be designed, and we thought the quantum cascade laser actually approaches very well the Shallow-Towns formula. Recently, two groups have found, both theoretically and experimentally, confirming that the QC laser actually has an intrinsic line width that is below the Shallow-Towns limit. I'm very much interested in the history of technology and science, and if you look back at all inventions, basically the ones that make it commercially, typically, there's usually a minimum of around 10 years. I mean, there are exceptions, of course. And I think the QC laser has started, in fact, to take off commercially 10 years later, 2004. Now there is almost around 20 companies, and the leading one is Hamamatsu Photonics. They have exhibits at Photonic West and Clio and so forth. There is a number. Alcatel has created a division. It's called 35 Laboratories that commercializes QC lasers. And there is a bunch of companies coming up, some startups, some beyond the startup point. So the commercialization is full swing. I think that the next decade is going to be really a decade of chemical sensing. Many are going to be enabled by the quantum cascade laser, both for threats, military, for the military scenario, but also for pollution monitoring. Most important, I believe, also areas like combustion diagnostic, medical diagnostics. We have shown that combining laser technology like quantum cascade laser, but not only QC laser, with plasmonics can deal to very interesting thing. We have shown that we can shape the beam of laser. So we have made multi-beam, multi-wavelengths quantum cascade laser. I think this is a unique feature, okay, the ability to have a laser to simultaneously launch multiple wavelengths in different directions of space. I mean, this is, of course, research, but it's very exciting.